this video, I'm going to go through the Princeton Review multiple choice and free response questions, and I'm going to explain all of them just to make sure that we're on the same page and you're clear about some of the key concepts. So for this first problem, it gives you reaction 1, and it asks you to determine the enthalpy for that reaction. Now notice it gives you 3 other reactions, so as soon as that happens, you should realize I'm going to need to add at least 2 of these reactions together, if not 3, in order to form reaction number 1. And so in this case, what I'm going to do is I'm going to look at my key players, and my key players would be ones that specific reactions have that are unique to them. So for example, reaction 2 has the N2H4 that we want for reaction 1, and no other reaction has it. So that tells me that's a key player, and therefore I want just one N2H4, and I want it exactly where it is, so I'm going to leave it alone. Another key player is your NH3. Notice your NH3, I've got 2 for my reaction 1, and I've got 2 for reaction 3. Therefore, that tells me I want to leave reaction 3 completely alone. Other important features, notice I didn't look at H2 simply because H2 exists in all 3 of the other reactions. So that might be a little intimidating, so instead I'm going to look and I'm going to say, okay, I have CH2O in reaction 2. And unless I get rid of it, that would end up in reaction 1, but I don't want it. And so that tells me I need to take reaction 4, and since CH2O is also a product for reaction 4, I need to flip reaction 4. So I need to multiply that by -1, and that gets rid of CH2O. If you then add up those 3 reactions, you will get reaction 1. Notice your 3 H2s cancel out. You've now got H2, just one H2 on your reactant side. Therefore, I have reaction 1. So all I need to do, just like what you did for your equilibrium constants, I need to take my delta H's, my enthalpies, and now instead of multiplying them like you did for your equilibrium constant, I need to add them. But before I do that, I need to take my enthalpy for reaction 4, and I need to multiply that by -1. Remember, for your equilibrium constant, you had to raise it to the -1. Now I'm just multiplying by -1. Now I'm going to add these up. So -37 plus -46 plus 65 gives me C -18 kilojoules per mole of reaction. In number 2, it says if reaction 2 were repeated at high temperature, what would the reaction's value for delta G, or how would it be affected? So I need to use my Gibbs free energy expression. Reaction 2, if you look at it, reaction 2, your delta H is negative. And if you look at reaction 2, I can actually determine whether or not my entropy is positive or negative. Specifically, if you look at this, notice for reaction 2, you go from having 2 moles of liquid to having 5 moles of gas. Okay, and I look at that, I determine that by looking at the coefficients. So that tells me my disorder, or my entropy, increased, making delta S positive. So if my temperature were to increase, notice delta H is negative, delta S is positive, if my T were to get even bigger, that would simply make my delta G even more negative. So the answer is A. For number 3, it says, under what conditions would the reaction 3 be thermodynamically favored? Okay, so in order to answer this question, I need to, once again, use my delta G, my Gibbs free energy formula, because remember, thermodynamically favored means your delta G is negative. So for reaction 3, my delta H is negative. Okay? If you look at this reaction for reaction 3, I have 4 moles of gas on my reactant side and 2 moles of gas on my product side. So what that tells me is that my disorder actually decreases, which means that my delta S is negative. So keep in mind, since I want delta G to be negative, delta H is negative, awesome, that's fine. But be careful, because since your delta S is negative, the minus and negative cancels it out and makes it positive. So in order to make sure that delta H has a greater impact, you need to make sure that that your T is going to be as small as possible. And therefore your answer is C. For number 4, it says if 64 grams of CH4O were to decompose via reaction 4, approximately how much energy would be released or absorbed? So keep in mind for this question, all of my enthalpies that are given to me are in kilojoules per mole of reaction, which begs the question, what is per mole of reaction? Well, if you look at reaction 4, for example, I have 1 mole of CH4O for every mole of reaction. I have 1 mole of CH2O for every 1 mole of reaction, and then I have 1 mole of H2 for every 1 mole of reaction. If you look at reaction 3, however, I have 3 moles of H2 for every 1 mole of reaction. And so in this case, it's actually the 1 mole of CH4O is the same thing as 1 mole of reaction, so it works out. But do be careful, because if you have a coefficient in front of a reactant or a product, the moles of that reactant or product will not be the same as the moles of reaction. So you would have to do one more conversion, okay? But not in this case. So in this case, what I can do is I can say, okay, I have 64 grams of CH4O. How many moles would that be? So I'm going to divide by its molar mass. That's 2 moles. Now I know it releases 65 kilojoules for every mole of reaction. I'm going to take the 65 kilojoules and I'm going to multiply that by 2, so that gives me 130. Now notice, because it's going to be negative 130, that would be positive 130 kilojoules of energy that are going to be released, because the released implies that it's going to be negative. So your answer is D. For number 5, it gives you this reaction. It says, during the reaction above, the product yield can be increased by increasing the temperature. Why is this effective? So how could I increase my product? Well, since my delta H is positive, that means that it's endothermic and it's on my reactant side. So if I increase temperature, I'm going to see a shift to the right, or it's going to proceed towards the products, as we have said in this class. And so therefore your answer here is actually just going to be A. In number 6, it gives you the reaction. It says the reaction above is not thermodynamically favored under standard conditions, but it becomes thermodynamically favored as the temperature decreases towards absolute 0. Which of the following is true at standard conditions? So once again, because I'm talking about a reaction being thermodynamically favored or not, I'm going to use my Gibbs free energy formula. I need my delta G to be negative. Okay? I don't know about my delta H, but looking at this reaction, since you go from 3 moles of gas and 2 moles of solid to 2 moles of solid, you know your delta S is going to be negative. Therefore, since you have a negative T delta S and your delta S is negative, that makes it positive. Okay? This problem is then saying it is not thermodynamically favored, but it can become thermodynamically favored if you decrease temperature. Meaning, since your T delta S, that whole value is automatically going to be positive since you have minus T delta S and negative delta S. Delta H, if you have the possibility of it becoming thermodynamically favorable, that means your delta H has to be negative. Because otherwise, if delta H were positive, that delta G would always be positive. You would have no way of making it negative. So instead, what that tells me is that my delta H is negative, which means my answer would be A. In number 7, it tells me I have 1.50 grams of sodium nitrate dissolving in 25 mils of water. It causes the temperature to increase, and I know the density, and then it's asking me to figure out the heat. Now, really quickly, whenever we're doing these calorimetry problems, keep in mind if you are dissolving a solid in water, then the mass is going to be the combined mass of your solute and your solvent. Now this problem is a little bit wonky because instead of just saying, hey, you've got 1.50 grams of NaNO3 and then you could figure out you have 25 grams of water simply because we know the density of water is 1.0, what they're giving you is the density of the solution. So to find the mass of the solution, instead of adding the solute and the solvent like what we've been doing, what they want you to do is say, okay, the mass of the solution is going to be about 25 mils because the solute's not going to affect the volume. Okay, so you have 25 mils of your solution. We're going to multiply that by the density to figure out the mass of your solution. That's your M and your Q equals MC delta T. We know your C is 4.18. Okay, that's a given. And we know your delta T is going to be 2.2 because that is also given. So your answer for this, since you're multiplying everything, and remember you multiply by density because volume times density, your milliliters would cancel out and you'd be left with just grams. So your answer, once you do all of this, is just going to be D. In number 8, it says a pure solid substance is heated strongly. It first melts and then it boils. Which of the following heating curves correctly shows that relationship? Okay, so this is something you should have learned in first year chemistry. We haven't officially gone over it, but the answer for this is A. So let me explain what's happening if you'll look at A really quickly. You start off when you're at 0, 0, right at your origin right there. You start off with a solid that's really cold. As you add energy to that solid, the temperature increases. And it's going to increase until it reaches that first shift where it plateaus off. That plateau happens at the melting point. The melting point, it's now going to go from a solid, and then it goes and becomes a liquid. Then that liquid at the end of that plateau, on the far right hand side of that plateau, that liquid will be heated even more because you're adding more energy, so the temperature will increase. Then you have a liquid at the very top that's at the boiling point. You'll go from a liquid to a gas, and then a gas and increase the temperature of the gas. Notice that plateaus then represent going from a solid to a liquid and a liquid to a gas. The reason why temperature doesn't change at those plateaus is because the energy that's being added, that's being used to break the attraction between the solid molecules and then to break the intermolecular attractions between the liquid molecules. So that's why you see those plateaus, because energy is being used not to increase temperature and have the molecules move faster, but for the intermolecular forces to be broken. So that's a heating curve, and you'll see a couple more problems like this throughout this review. So make sure you're comfortable with that. For number 9, it gives us a reaction, all right, and it gives me the overall reaction, and it tells me, okay, find your enthalpy. Now, this is just like the first problem we did, so let's look for major players. My first major player is CH4. So I know that that first reaction is going to have to be flipped, because right now CH4 is a product and I want it to be a reactant. So I'm going to multiply that by -1. Another major player is CO2. CO2 is already a product for the second reaction, so I'm good, and it's the correct number. Another major player is H2O, because the third reaction is the only reaction with H2O. I need to take that entire reaction, and I need to multiply it by 2, though, in order to get 2 water molecules. If you add all of those up then, after you've looked at the major players, just to double check, you'll find that you actually have that final reaction that you're looking for. So then this is going to be 2Z plus Y minus X, since I add up my heats, and therefore the answer is D. In number 10, it says a student studies 2 solutions. Solution A has a volume of 100 mils, and it's at a temperature of 25 degrees Celsius. Another one has a solution B, so it has 1,000 mils, and it has a slightly lower temperature. Which of the following statements must be true regarding both solutions? All right, solution A has more heat than solution B. Okay. Well, when we're talking about heat, we're talking about the transfer of energy. So one solution can't have heat. It is transferring the energy, and that is heat. So answer A doesn't make sense. Specific heat capacity would be Q equals MC delta T, but this problem hasn't told me anything about the change in temperature, so I don't know. Okay. It says for the next one, heat would be transferred from B to A. That's not true, because B is actually at a lower temperature. Heat would go from solution A at a higher temperature to solution B, which is at a lower temperature. So the final answer, the only one that works, is that solution B has more thermal energy. Okay, so it has more thermal energy not because it's at a lower temperature, but because there's such a great volume of solution B that it's going to have more overall energy. It's going to possess more energy. In 11, here it's asking me to find my enthalpy change. Now notice we're using my bond energies. So remember, unlike heats of formation where I do products minus reactants, for this problem, I'm going to do reactants minus products. And remember, I do that because I need to break the reactant bonds, and then I need to form the product bonds. When I break the reactant bonds, that is represented by the bond energy, because the bond energy is the energy needed to break a bond. For forming the product bonds, I need to make that negative simply because that is releasing energy when I form bonds. So when I look at this, I know H2 would just be H bound to an H, a single bond. So it's going to be 2 times that bond energy, plus the energy needed to break a double bond for oxygen, okay, minus, well, here's the thing, be careful with this problem because I have 2 water molecules, so that's what that first 2 represents, but then every water molecule has 2 oxygen-hydrogen single bonds. So I have a total of 4 of those OH bonds that need to be formed. So I take 2 times 500 plus 500 minus 4 times 500, okay? And what I get is negative 500 kilojoules, which would be B. In number 12, it tells me that water liquid is becoming a solid. Okay? Whenever you have a state change from liquid to solid, solid to liquid, liquid to gas, gas to liquid, I am at equilibrium. And if I'm at equilibrium, I know my delta G is going to be 0. So that's your answer. For number 3, it says which point on the graph shown above corresponds to the activated complex. Remember, the activated complex is that transition between your reactants and your products. It has the highest potential energy, therefore it's going to be 3, so it's going to be C. For number 14, it says the distance between which 2 points is equal to the enthalpy change for this reaction. Okay, remember number 1 represents where I start with my reactants, number 4 is where I finish, therefore the change in enthalpy is going to be the difference between point 1 and point 4. What would happen to this graph if a catalyst were added? Remember, a catalyst lowers your activation energy, which tells you that point 3 would be lower because that's lowering your activation energy, so your answer is A. In 16, once again, I have to manipulate these reactions, so let's look for my major players. So first, notice I'm going to look at that first reaction right there. I've got carbon dioxide as a product, which is great, but I only have 1 carbon dioxide. So that tells me I'm going to have to multiply this reaction by 2, which means I'm going to have to multiply my enthalpy by 2 as well. Okay. For my next step, notice water is a product. There's 1 water there, and there's 1 water for my final reaction, so I'm fine with that guy. The next major player is your C2H2. Notice it's on your product side up above, but then on your reactant side for your final reaction. So I need to flip that reaction by multiplying by -1. So I'm going to multiply this by -1, and all I have to do is add up all those enthalpies, so negative 390 times 2 plus negative 290 minus 230, and so what I get for an answer is negative 1,300 kilojoules. For number 17, it says, in which of the following reactions is entropy increasing? Okay? So if I look here at A, I go from 3 moles of gas to 2 moles of gas. That's a decrease in entropy. For B, I go from 2 moles of gas to 2 moles of gas. That's no change in entropy. For C, I go from 2 moles of gas to 2 moles of gas. No change in entropy. And then finally in D, I go from 2 moles of gas to 3 moles of gas. So my answer would be D. For 18, it says, consider the following reaction showing photosynthesis. Which of the following is true regarding the thermal energy in this system? Okay? So since this is an endothermic reaction, remember for an endothermic reaction, energy is required by the reaction. And it comes from the surroundings. So your answer is going to be A. It's transferred from the surroundings to the reaction. If it were exothermic, it would go from the reaction to the surroundings. In 19, it gives you the reaction, and it says gaseous hydrogen and fluorine combine in the reaction above to form hydrogen fluoride with an enthalpy change of negative 540 kilojoules. What is the value of the heat of formation of HF? Okay, so remember, my formula for my enthalpy change is going to be my products minus my reactants. So my enthalpy change is the difference between my heat of formation of products minus the heat of formation of my reactants. Since I know my delta H is negative 540, that leaves the question, okay, I'm trying to figure out my delta H of formation of HF. What about H2 and F2? Well, remember, since you're under standard conditions, the delta H of formation for those guys is going to be 0. So what that creates is this formula here. Negative 540 equals 2 times my heat of formation of products minus 0. And so I can solve for my heat of formation of my products, and I get negative 270. For number 20, it says when calcium chloride dissolves in water, the temperature increases dramatically. So that means that it is an exothermic process. Remember, you've got 3 things that are involved in dissolving. Solute-solute interactions have to be broken, which makes it endothermic. Solvent-solvent interactions have to be broken, which is also endothermic. And then finally, once all of those are broken, solute-solvent interactions can occur, and that attraction is exothermic. So since this is an exothermic reaction, that tells me that that interaction between the solute and solvent is stronger than those two other attractions. Therefore, my answer is B. The hydration energy between water molecules in the solute exceeds the lattice energy within CaCl2, and also the attraction between water molecules themselves. In 21, it says, during this reaction, heat transfers from what to what? Well, since this is an exothermic reaction, that means it's going from the reaction to the surroundings. So it's going from the system to the surroundings. My answer would be C. In 22, it says, which is the primary driving factor behind this reaction? Okay, so if you look at the reaction in 22, okay, we need to figure out if my enthalpy is positive or negative, and then if my entropy is positive or negative. So if I look at this reaction, number one, I'm going to be using delta G equals delta H minus T delta S. I know my delta H is negative because it told me my reaction was exothermic. If you look at this process, since calcium chloride is dissolving, whenever a solid dissolves in water, that's going to increase the entropy of a reaction. So that's going to be positive. So what's the major driving force? Well, both enthalpy and entropy, because they both help in making delta G negative. In 23, it says, compared to calcium chloride, what must be true regarding the hydration energy of calcium fluoride? So this is something we're going to get into extensively with Big Idea 2, but just open your mind to the idea. So, calcium fluoride. Fluoride ions are much smaller than chloride ions, which means that because fluoride ions are smaller, the smaller an ion is, the better able it is to attract either other ions or water. So the smaller, the better. So therefore, since fluoride ions are smaller than chloride ions, that means that the hydration energy, right, the attraction between the fluoride ions, once they've broken from calcium ions, and water is going to be greater than with the chloride ions simply because fluoride ions are smaller. So keep that in mind, re-listen to that if you had trouble with that, and we will also look at that again in Big Idea 2. Finally, for 24, it says the reaction shown in the diagram below is accompanied by a large increase in temperature, meaning it is exothermic. If all molecules shown are in the gaseous state, which statement accurately describes the reaction? So we know it's exothermic, so we can get rid of C and D. If we look at this, I have 3 moles, or 3 molecules, of my N2H4, and then that produces, and all of these are gases, by the way, I go from 3 molecules to having 1, 2, 3, 4, 5 molecules, which tells me my entropy, my disorder, is increasing. So not only is it exothermic, but my entropy increases, so the answer is A. So that's all the multiple choice. I would go back and re-listen to problems that you had issues with, and then, so pause me, and then I'm going to just continue on with the free response right now. Okay? So let's look at the free response. For number 1, it says energy is released when glucose is oxidized in the following reaction, which is a metabolism reaction that takes place in the body. It first wants you to calculate the standard entropy change for this reaction. So I need to take my entropies that are given to me, and I need to take the absolute entropies, and I need to do products minus reactants. So what I'm going to do is I'm going to take 6, multiply it by the absolute entropy of CO2, which is 213.6, and I'm going to add to that the entropy of water, so 6 times 69.9. Then I'm going to subtract from that the entropy of my reactant, so 212.13 for my glucose, plus 6 times the entropy of oxygen. And so when I do that, I end up getting 259. Now, I disagree with their units. Because you've multiplied by your coefficients, your unit should not be joules per mole Kelvin. It should just simply be joules per Kelvin because you've already multiplied by moles. So that's A. And B, it says calculate the standard free energy change, delta G, for the reaction. Well, since I know my entropy and I know my enthalpy, because it's given to me, I can calculate this. Now you do need to be careful because notice your entropy is in joules, your enthalpy is in kilojoules. So what they did for this problem and what I would do is I would convert your entropy into kilojoules by simply dividing by 1,000. Then plug in your values and you can calculate your delta G, which is negative 2,880 kilojoules per mole of reaction, or just per mole is fine to write as well. Okay, so that's B. In C, it says, using the axis below, draw an energy profile for the reaction and indicate the magnitude of delta H. Okay, so since this is exothermic, the heat of your reactants needs, or the energy of your reactants needs to be higher than the final energy of the products, otherwise it doesn't really matter. And you need to show that your enthalpy change, or your delta H, is going to be the difference between your reactants and your products. Okay? For the final question, it says, how much energy is given off by the oxidation of 1 gram of glucose? So that's what I start with, 1 gram of glucose. And in order to use my enthalpy, which is in kilojoules per mole of reaction, I need to get into moles of reaction. So I'm going to take 1 gram of glucose, I'm going to divide by the molar mass, that gets me into moles of glucose. Then notice, as I had said in the multiple choice, there is 1 mole of glucose for every 1 mole of reaction. If, just really quickly as a side note, if I were to do oxygen, it would be 6 moles of oxygen for every 1 mole of reaction. So while in this case it doesn't affect your answer, be careful just in case it will. So now I'm in moles of reaction, then I can use my enthalpy, whose units are kilojoules per mole of reaction, multiply by that and get my overall energy that's involved, which would be negative 15.5 kilojoules. And that's it. For number 2, it wants you to use the table of bond dissociation energies to find your delta H. So remember, as I said in the multiple choice, because you are breaking bonds first, and that's what your bond dissociation energy represents, you're going to do reactants minus products, because energy is released when you form your products, which means all of those bond dissociation energies need to be made negative. Okay, so you're going to take your bond dissociation energy of CH. Now be careful because CH4 has 4 CH bonds, so that's why they multiply by 4. So it's 4 times 415, plus you have your oxygen. Now for each O2, you have 1 O double bond O, but because you've got 2 moles of that, it's going to be 2 times that bond dissociation energy, which is 495, and you're going to subtract from that 2 times the bond dissociation energy for a carbon double bond to oxygen. And you do that because carbon dioxide has 2, each carbon dioxide has 2 carbon-oxygen double bonds. Then you're going to add to that the bond dissociation energy of OH, a single bond, but keep in mind you've got 2 OHs in each water and you've got 2 waters themselves, so that's going to be a total of 4. Okay, so that's how they got all of those answers. When you add them up and subtract, you get negative 800 kilojoules per mole, and that's your answer. Now, I think it's fine to just say kilojoules and not kilojoules per mole. They won't take off for that. Okay. For B, it says how many grams of methane must react with excess oxygen in order to release 1,500 kilojoules of heat. So that's my given. I start with 1,500 kilojoules. I use the enthalpy that I calculated, the negative 800, so I'm going to divide by 800 kilojoules, and I'm going to put that underneath 1 mole of CH4, because I know that 800 kilojoules are going to be released whenever 1 mole of CH4 reacts. Okay, that gets me moles of CH4. Now that I'm in moles of CH4, then I can get into grams of CH4 by multiplying by the molar mass of CH4. So keep in mind for these problems, whether you're giving grams or kilojoules, you're being able to use your enthalpy, which is in kilojoules per mole, in order to do some more stoichiometry. Okay? So there's your answer there, and it's 1 sig fig is 30 grams. Now, if you have a different number of significant figures, because I'm not sure if you got exactly 800, I kind of disagree with their sig figs here. I would say you should have 3 sig figs, so it should be negative 800 point if that's exactly what they got, and then have your answer for grams be in 3 sig figs. That would be my opinion. Okay. For C, it says, what is the value of delta S? Well, since I know my delta H and my delta G, which was given to me, I can calculate my delta S using my Gibbs free energy formula. Now, they set it up this way. You can simply just plug in numbers, plug and chug. Okay, notice they don't ask you to be in joules per Kelvin. Specifically, you could be in kilojoules per Kelvin, so you could leave it as 0.003 or whatever it would be to the correct number of significant figures. For D, it says, give an explanation for the size of the entropy change. Well, the entropy change is really, really small. It is positive, but it's really small. And the reason why is because if you look, you're not changing the number of moles of your reactants or your products, right? You have 3 moles of gas and 3 moles of gas on both sides. Therefore, the only reason why you have a change in disorder is simply because of the arrangement that's occurring. Okay, so the entropy change would be really small simply because you're not changing the moles of gas, and therefore you'd have a very, very small change in entropy, if not no change. I would have predicted no change at all, so that's why it's so small. Okay. For number 3, gives you a heating curve again. Awesome. So let's work with that again. It says the diagram above shows how the temperature of a certain covalent substance changes as heat is added to it. What is greater for the substance, the heat of fusion or the heat of vaporization, and how do you know? Well, if you look, the first plateau represents your heat of fusion, your heat required to melt a substance. The second plateau is your heat of vaporization, the heat required to vaporize a substance. So based on the fact that that line, that plateau is longer, you know that the heat of vaporization is higher. Now, it makes sense why it would be higher, because in order to go from a solid to a liquid, yes, intermolecular forces, the attraction between your solid molecules, have to be broken. But to go from a liquid to a gas, that requires even more energy, because you're not only having to break some of the attractions, you're having to break all of them to create a gas. So your heat, I would make a note to yourself, your heat of vaporization is always going to be higher than your heat of fusion, simply because you're going from a liquid to a gas, which requires a lot more heat. In B, it says if additional heat is added to the substance, the line would continue as its current slope and never become horizontal again. Why? Meaning the very last line that you see that has a horizontal slope. Well, that's because there are no other states of matter other than solid, liquid, and gas for the purpose of this class. So that what would happen if you kept adding energy to this is it would simply, your gas would just get hotter and hotter and hotter and hotter. Okay? For C, it says, reading the graph above, a student theorizes that the specific heat capacity of the substance is greatest in the solid phase. Do you agree? So let's compare solid versus a liquid versus a gas. Notice the slope of this graph. Remember, it's going to be rise over run. However, if we're considering your specific heat, to find your specific heat, you would take your heat and you would divide it by temperature. So it's actually going to be flipped. So the greater your specific heat, the more level your slope is going to be, the shallower your slope is going to be. Because that means, if you look, for example, at the slope for example, your gas, right? Your gas increases in heat more than any of the other two of them in less temperature that's required. So more heat is required with less temperature. So if you think Q equals MC delta T, your C, the larger your specific heat, the less temperature change is occurring, but the greater the heat gain or loss is, because Q equals MC delta T. So your C, the larger your C, the more heat change you have versus temperature change. So the steeper the slope is for these graphs, the less the specific heat is going to be. What would the signs be for the enthalpy and entropy changes as heat continues to be added? So if I'm adding heat, that means that my enthalpy is positive. It's endothermic. I'm adding heat to the system. Now, if I'm going from a solid to a liquid to a gas, I also know that my entropy is going to be positive because I'm increasing the disorder of that system. Because remember, gases have much more disorder than solids do. So both of them would be positive. Okay. For number 4, it says for the boiling of methanol, you have a delta H of positive 37.6 and an entropy of positive 111. Why is the delta H positive for this process? Well, whenever I go from a liquid to a gas or a solid to a liquid, that state change requires energy because intermolecular forces are being broken. So since energy is required to break those attractions, it's going to be endothermic. So a good way to think about it, if you're looking at that heating curve, I would make a note to yourself, if you move from left to right, it's going to be endothermic, meaning you're having to put energy in. If you move from right to left, it's going to be exothermic. So for example, if you're going from a liquid to a solid and freezing, your enthalpy change would actually be negative. Or if you're going from a gas to a liquid, your enthalpy change would be negative. For II, it says, why is the delta S positive for this process? Well, a gas has more disorder than a liquid does. Okay, so therefore your delta S is going to be positive. What is the melting point of methanol in degrees Celsius? Well, to figure out your boiling point, remember your delta G has to be 0 when you have a state change because you're at equilibrium. So I'm going to use my Gibbs free energy equation. I know my delta G has to be 0 because I'm at equilibrium. My delta H was given to me as 37.6, and my S, my entropy change, is 111. You need to convert that into kilojoules, okay? And then I'm going to just plug that in and solve for T. So I get, for my temperature, 339 Kelvin. Remember, it does ask it in degrees Celsius, so I'm going to subtract 273. If you get 66, that's fine. It doesn't have to be 65.9, because we use 273 in our class. In C, it says how much heat is required to boil 50 mils of ethanol if the density of ethanol is 0.789 grams per mil. So, for this problem, I need to figure out the mass of ethanol, and I do that by simply multiplying your volume by your density. Then, since I know my mass of ethanol, I can use my delta H to solve that problem. Okay, so I need to go from grams of my ethanol, I need to figure out the moles of ethanol, and for moles of ethanol, I can then multiply by the enthalpy, because remember it's kilojoules per mole, and that will give me my heat change, which is 46.2 kilojoules. For the next one, it says, what will happen to the temperature of the methanol as it boils? Nothing. It does not change. Because remember, all the energy that is being added is being used to break intermolecular forces, or those attractions. So the kinetic energy of the liquid is not going to change at all. It's going to stay the same, because all of those intermolecular forces have to be broken first. Then, once those intermolecular forces are broken, then the temperature can increase further. Okay? Would the methanol be soluble with water? Okay? So if you look at methanol, this is something that we looked at briefly. You definitely looked at in first year chemistry. If you look at methanol, you have CH3OH. Remember, if you have a molecule, if you were to draw out the Lewis structure in which everything were to cancel out, all your dipoles were to cancel out, meaning it would be perfectly symmetrical, and you'll look at this more in Big Idea 2. But if it were perfectly symmetrical, it would be nonpolar. But since the dipoles do not cancel out because it is not symmetrical, CH3OH is going to be polar. Therefore, it will be soluble in water because polar molecules dissolve polar molecules. Okay? They don't like on the AP saying like dissolves like. I'm not sure why they use that explanation here, but I would say a polar molecule will dissolve a polar molecule, and you're good. Would you expect the boiling point of ethanol, which is CH3CH2OH, to be less than, greater than, or the same as methanol? So again, this is something that you're going to get from Big Idea 2, but you guys can totally do it. When you're comparing compounds that have the same intermolecular force, so CH3OH and CH3CH2OH both have hydrogen bonding, and we'll get to that, don't worry. But what you need to keep in mind is the fact that CH3CH2OH, the difference between that and methanol is the fact that ethanol is actually larger. Now, what's important is that since it is larger, it has more electrons. And since it has more electrons, it is more polarizable. So the larger, if you have a huge molecule, regardless of the type of intermolecular force you have, since it is so big, we say it has more electrons, therefore it is more polarizable. So make another note to yourself. If you have a really big molecule, it's going to have a stronger intermolecular attraction because it's bigger, because it has more electrons, therefore it's more polarizable. Okay, so since ethanol has stronger intermolecular forces, that means it's going to take more to actually get it to go from a liquid to a gas. You're going to have to provide more heat. Therefore, it's going to have a higher boiling point. And we'll get to hydrogen bonding and London dispersion forces in Big Idea 2. But this actually should be reviewed from first year chemistry. You should remember hydrogen bonding, LDF, and dipole-dipole forces. The main thing is, regardless of the type of bonding you have, if something is a lot bigger, it's going to have a stronger intermolecular force because it has more electrons, making it more polarizable. The fact that, a really important thing also is the fact that both of those compounds have hydrogen bonding. But what sets ethanol apart is that it is bigger, therefore stronger intermolecular attractions, therefore a higher boiling point. We're now on number 5. Ammonia gas reacts with dinitrogen monoxide via the following reaction. Okay, so it gives you the entropy values. It says calculate the entropy value for the overall reaction. So again, just like with entropy, enthalpy, Gibbs free energy, you need to do products minus reactants. So you'll do 3 times the entropy for water, plus 4 times the entropy for nitrogen, minus 2 times the entropy for NH3, plus 3 times the entropy for N2O. You'll solve this. Remember, it's going to be in joules. I disagree with their units. I think it should be 289 joules per Kelvin, but if you want to put joules per mole Kelvin, that's fine. For B, it gives you the bond enthalpies. Okay, so calculate the enthalpy for the overall reaction. So I like how they draw this out for this answer to help you to actually be able to understand it. Notice here you have 2 NH3s, so you'd have a total of 6 NH bonds that have to be broken. For the next one, you have 6 NO double bonds that have to be broken because you have 3 and then you got 2 in each of the molecules. For the products, you now subtract 4 times your bond enthalpy of N triple bond N, and then you would add to that 6 times the bond enthalpy of OH because you got 2 OHs in each water and 3 waters. So the math for that boils down to this. Okay? And so you have your delta H ends up being negative 434 kilojoules per mole. Okay. For C, it says, is this reaction thermodynamically favored? Justify your answer. Okay. So once again, to figure out if something's thermodynamically favored, if you're not given delta G, you need to use your Gibbs free energy. We know our delta H now. We know our delta S because we calculated it. Just make sure you convert joules to kilojoules. You can calculate this. You know what temperature it happens at, so it's negative 520. Since delta G is negative, yes, it is thermodynamically favored, meaning it is spontaneous. In D, it says if 25 grams of NH3 reacts with 25 grams of N2O, will energy be released or will it be absorbed? Well, since your delta H is negative, we know this is an exothermic reaction, therefore energy is going to be released. It then wants to know the magnitude of the energy. Well, here's the problem. It gives me 2 different reactant values, the amounts of my 2 reactants. So I have to figure out how many moles I have and therefore then be able to use my enthalpy. So what I can do is I need to convert into moles of my reaction to then multiply by the negative 434. So I'm going to take each of these, my mass of each of my reactants, divide by their molar mass. Then notice, for example, for NH3, since the coefficient for NH3 is a 2, that tells me that I have 2 moles of NH3 for every 1 mole of reaction. Okay? So I'm now in moles of reaction. I can then multiply by my enthalpy. That gives me negative 318 kilojoules. I do the same thing with N2O, except now I have 3 moles of N2O for every 1 mole of reaction. That gives me negative 82 kilojoules. So whichever one's smaller, that's the amount of heat that's going to be released, because only 25 grams of N2O can be used. The 25 grams of NH3 is going to be in excess, so it's not going to release all that energy. You look at your limiting reactant. Even though we are talking about heat, we're still dealing with a limiting reactant problem. So it's negative 82 kilojoules. Okay? In E, it says on the reaction coordinates, draw a line showing the progression of the reaction. Okay, so you can see that below, making sure that your reactants have more energy than your products do. It wants you to show the activation energy, so that would be that first hump that you got to go over. So from the reactant's energy to the transition state, so that difference. And then also wants you to show your delta H, which is drawn in that diagram. Last one. In 6, it says a student designs an experiment to determine the specific heat of aluminum. The student heats a piece of aluminum with a mass of 5.86 grams to various temperatures, then drops it into a calorimeter containing 25 mils of water. The following data is gathered during one of the trials. All right, given the specific heat of water and assuming its density is 1 gram per mil, calculate the heat gained by water. So be careful with this problem because this can confuse students a lot. Remember, unless a solid is being dissolved into water to create a solution, you are not going to add the masses. Okay, so in that case you do. In this case, because you're adding aluminum to water, the aluminum is not going to combine with the water. So you're going to treat the two separately. You have aluminum, which is at a high temperature, transferring heat to the water. And you have water accepting the heat from the aluminum. So the heat that's involved for the water transferring to the aluminum and the aluminum accepting from the water, those are going to be equal but negative, as you'll see. So let's first look at 6a. So I'm going to use Q equals mc delta T. I know my mass of water is 25 because my density was 1 gram per mil. I know my specific heat and I know my change in temperature is 3.6 because the initial temperature of water was 23.2 and the final is 26.8. So I'm able to calculate my Q. My Q is 376 joules. Now, the heat that the water gains, that equals the heat that the aluminum lost. So my Q in B, when it's asking me to find the specific heat of aluminum, my Q is just going to be negative 376. Okay? I know the mass of aluminum that's given to me in the problem, okay, 5.86. I know my change in temperature because initially it was 109.1 and then it became 26.8 after it was added to the water. So I know my change, remember TF minus TI, so it's negative 82.3 degrees Celsius. I can now solve for C. So what I get for my specific heat is 0.780 joules per gram degrees Celsius. So just as a quick review for your changes in temperature, water goes from being 23.2 to 26.8. That's why your delta T is positive because it's TF minus TI. While your aluminum goes from 109.1 to 26.8, which means that your delta T would be negative because it's losing heat. Okay. For C, it says calculate the enthalpy change for the cooling of aluminum in water in kilojoules per mole. Okay. So I need to figure out the enthalpy change for aluminum specifically. So I need to figure out the mass of aluminum, which was 5.86. I need to get that into moles. So I'm going to divide by the molar mass of aluminum. That's 0.217. Okay. Then I can take that and use it, take the 376, divide it by 0.217, and now I'm going to be in joules per mole because it's asking me for kilojoules per mole. Then I can simply convert that into kilojoules per mole by dividing by 1,000. So it's 1.73 kilojoules per mole. If you want to put that as a negative 1.73, I don't see any issue with that. But they put 1.73, I probably would have put 1.73. But if you thought that the heat was negative 376 joules because it's being lost and divided by the moles, then you would have gotten a negative value, and that should be fine. Okay. For D, it says if the accepted specific heat of aluminum is 0.9, calculate the percent error. Remember, percent error is experimental minus accepted, the absolute value of that, divided by your accepted. So the experimentally you got 0.780. Subtract from that your accepted, divide by your accepted, and you get 13.3% error. All right, sources of error. Now, there are a number of different sources of error. Notice in the answer that you got, if we go back a slide, your experimental is less than your accepted. Okay, so what could be some causes for this? All right, so let's look at this and really understand what's going on. So, if I take the hot aluminum and I add it to water, in that transfer of the aluminum from where it was heated to being put into water, if it lost heat, your Q would be too small, which means when you calculate your C for aluminum, since your Q is too small because it lost heat, that means that your C is going to be too small. So that could be a possible reason why your specific heat was lower than it should have been. Another reason could be, for example, the fact that the calorimeter is not perfect, and the calorimeter itself could have absorbed energy. So if the calorimeter absorbed some of the heat that was transferred from the aluminum to the water, that could cause your Q that you measured to be smaller than it should have been because your change in temperature of the water would have been less. So again, since your Q is smaller, that could cause the specific heat to be too small as well. That could be another source of error. The other source of error that they noted, which I thought was interesting, was that what if you added too much water to the calorimeter in the first place? What that means is that the temperature change you would see would be too low, simply because you're trying to heat up more water than what you thought you were supposed to heat up, which means the Q, the heat that's gained by the water, would be too low. I disagree with their argument that it would cause the mass to be artificially low. It would cause your Q to be too low simply because you have too much water, therefore the change in temperature you calculate is going to be less because you're having to heat up more. If your Q is too small, again, your Q, the heat that the water gains, is too small. That means that the heat that the aluminum lost is also too small, which means your specific heat is going to be too small as well. So all of those are different things that you can use to explain why your specific heat of aluminum was smaller than it actually should have been.